Hello everyone. Artificial Intelligence and Machine Learning Unit 5 Neural Networks. In this video, the topics are back propagation and shallow to deep neural networks. The objectives of this video preparation is to learn, understand and analyze back propagation algorithm and distinguish between shallow and deep neural networks. First we see back propagation algorithm. This is a typical neural network. X1, X2, Xn forms the input layer. This one forms the hidden layer, first hidden layer, and this one forms the second hidden layer. The green one forms the output layer. So each neuron, each node consists of two. One is the pre-activation and one is the activation. First is pre-activation. Pre-activation is mere accumulation of the inputs plus the bias. Bias present in that layer plus the weights multiplied by the output we obtained from the previous layer. So activation of the layer I is given by hi equal to g of ai of x. Whatever this is the input to this activation, g of what is g? G is activation function. Activation function can be a logistic or sigmoid or tanh, linear or softmax function or ReLU function. So different activation functions are there. The activation of the output layer will be generally be different. It depends on the application which you are using. Okay, HL of x equal to output of AL of x. This is AL. AL is the pre-activation at the output layer. So this is fed as input. So pre-activation output of output activation function will be softmax or linear. So normally the softmax will be used as the output activation function, not in the intermediate activation function. It's always used as a softmax is usually used for classification problem. So simplify the rotation. AI is denoted as A of x denoted as AI, HI of x denoted as HI. So now we have the data, label data for xi is assigned to yi. So we have a data here xi, yi, and how many we have? We have n, capital N, and the modeling is first we have w1 of x plus b1 at the first layer pre-activation, w1 of x plus b1. So g activation. Then this is fed as input to the first hidden layer. This is fed as input to the the second hidden layer. So what we will have, that will w2 multiplied whatever you get as the output of the first hidden layer. That is what? This is what? h1. So w2 multiplied by h1 plus b2. Similarly w3 multiplied by h2. This is what? h2. So h2 plus b3. So output of that, this output will be generally be a softmax function. So parameters will be w1, b1, b2. These are all the learnable parameters. These are called the model parameters. So what is LE? L equal to 3 here. 1, 2, 3. So normally we ignore the input layer because no computation is done at the input layer. Gradient descent algorithm is gradient descent with back propagation algorithm. So objective function, loss function. How do you calculate the loss? Loss is the actual value, the difference between the actual value and the value that is predicted by the model. Okay, you have to square it, sum it, and you have to find the average. You have to minimize this average. So cross entropy and softmax. Cross entropy is the loss function. The softmax is the output activation function. This is the softmax function. First we see what is cross entropy. The loss function summation c is equal to 1 equal yc log yc. So this yc would be yc cap is the predicted one. The predicted that is given by the model. Yc is the true value. That would be 1 for only one case. So for c is equal to n and 0 for the otherwise. So L of theta would be what? So only for one case it will be 1. So rest of them will be 0. So for if L is that case, if the L is the label, L is the actual label, then YL you get. So for YL that will be what? 1. So 1. So log of what? YL cap. That is YL cap is the value predicted by the model. So you will get minus log YL cap. What about softmax function? This is the pre-activation WL HL minus 1 plus BL. Output of price will be e power ALJ plus summation of ALI. Softmax gives the probability. It converts a real number into a probability distribution. It converts a real number into, when you sum all these values, that will give you what? 1. That will give 1. Which loss function and output activation function we have to use? So output activation function, if we use real values we have to go for what? Linear. And if you want probabilities, to get probabilities we should go for what I already said, softmax function. The loss function for real values we have to use squared error, and for probabilities, you have to go for cross. Wherever you use softmax as output activation, you have to use the loss function as what? Cross entropy. Back propagation in a thin network. First we see a thin network, very thin network. X1 is the input, this is the first hidden layer, second hidden layer, the output. A very thin network. So what's the loss function? Loss function L of theta. Now we are going to differentiate with respect what change I will have in the loss function if I give a small change in W111. How do you interpret W111? The first one refers to the layer number. The second one and the third one refers to the node number. Okay, I'll explain. Okay, you can see here W111 means W111. The first one refers to the first layer. Okay, the second one refers, this is the first node. The third one refers to the node number in the next layer. So when I say W111, that means what? It connects the first node in the first layer with the first node in the second layer. W112 means it connects the first node in the first layer with the second node in the second layer. Okay, this is how you have to interpret the terminology notation. So dou L of theta by, just use a simple chain rule. Dou L of theta by dou y cap, then AL111, then from AL1 to S21, S21 to A21, A21 to H11, A21, from A21 to H11, from H11 to A11, from A11 to W111. You can you can keep H11 alone. You can simplify this, what you get, dou L of theta by dou H1. You can compress the chain rule. Similarly, you can do the others. So I have used a softmax loss function here. So loss function is minus log YL cap. So according to back propagation theorem, back propagation algorithm, the loss that is accumulated at the outputter is contributed by all the nodes, not by the single node alone. Is contributed by all the nodes. We have to find which is giving more weightage, which is giving more change to the loss. So how do you do that? You have to find the gradient. So gradient of the loss function with respect to W1. What does it mean? A small change in W1. What you are measuring, how much change happens in the loss function. Okay. The chain rule, gradient with respect to output. Chain rule, we have three cases. One is gradient with respect to output units, then with respect to hidden units, then with respect to weights and the biases. Dou L of theta by dou W111, that is the change in loss function with respect to the change happens in W111. Now you first talk to the output layer, So y cap present the output layer, y cap A3. Assume that you have three layers, first hidden layer, second hidden layer, and the output. A3, 3 refers to the output layer, and 2 refers to the hidden layer, 1 also refers to the first hidden layer, second hidden layer, then the output layer. First you talk to the output layer, so y cap, then A3, then A3 to H2, H2 to A2. This is the previous hidden layer. Then the previous hidden layer, A2, H1, A1. So A1, then W11. This is how you have to reach the weights. This is called back propagation using chain rule. First you do the forward propagation, then you have to back propagate the error. Gradient with respect to weights. So how do you write AK? AK is bias plus WK HK minus 1 in the previous layer. So dou K minus 1 by dou W ij hk minus 1j. So is just you find the first derivative wk minus 1. What do you get? You get hk minus 1j dou L of theta by dou Wn. You can split that dou t. You can apply the chain rule akj by wkj. Just you can substitute here. Now you can obtain a matrix for the gradient del wkl of theta. So k111, the first node in the one layer and the first node in the next layer. 1 2 means the first node in that layer and the second node in the next layer. Okay, this is how we can complete the matrix. Then gradient with respect to bias. So aki bkj, now you are computing the gradient, that is how what change that happens in the loss function if you give a change in the bias. So that you can write it as dou L of theta by dou ki by dou bki. Okay, so dou ak by dou bk, just you find the derivative, what you will get here 1. You can substitute here. Now you can write the gradient with respect to a vector. First you find with the change with respect to a single element, then you represent in the form of a vector matrix del bk L of theta. Loss function is with respect to ak1 ak2 akn. Okay, then all gradients is gradient with respect to output layer, you will have al. Gradient with respect to hidden layer, you will have what hk and ak. And how many layers I will have 1 to L. Gradient with respect to weights and the biases, we are having only one output layer. How many hidden layers? 1 to L with respect to weights and the biases. So we will have weights and the bias in each layer. So wk and del vk. So back propagation algorithm. So using gradient descent back propagation algorithm, you have maximization 1000, initialize the weights, then you give the condition of iteration, then you have h1 h2 forward propagation you do, then you do the back propagation. First you do the forward propagation, you compute the loss and you find the derivatives and compute the back propagation. Okay, you compute the derivatives, then using the derivatives just you update the weights. What is the role of back propagation? We are fine tuning the weights and the biases. With the weights and the biases are the model parameters which are going to learn. Through back propagation we are fine tuning the weights and the biases. So first we have forward propagation ak bk wk hk, pre-activation, then activation, then you have to do for all the hidden layers. Okay, and for the output, this is for the output layer, al equal to bl wal kl, the y cap of o of al, this is for the output layer. Then you do the backward propagation. Now you compute the loss function. You have the loss function, you find the gradient of the loss function with respect to what? Al, this is with the output layer. Okay, then you for kl is equal to 1 to do compute the gradients with respect to parameters, then compute the gradients with respect to each layer, compute the gradients with respect to layer below for the pre-activations. This is how you perform back propagation. Now I will give an example here. This is an input layer, W1, W2, W3, these are the weights, H1, H2, this is the one hidden, we have only one hidden layer, and B1 is the bias, and we have an output layer. This is the target value. What is the actual value for Y1? The output of Y1 is 0.01, 0.099. This is ideal values. Okay, and we try to achieve these values using a model. Okay, now this is the reference. So input values x1, x2, they are given. X1, x2 given, W1, W2, W4, W5, everything is given. Bias values are given, target values, these are the target values. These are the actual values. We are going to find now predicted values. First we do the forward propagation, then you do the backward propagation. First you do the forward propagation, compute the loss, then you do find the gradient and back propagate the error and fine tune the weights and the bias. This is how you should proceed the back propagation. Forward propagation, to find the value of h1, first you multiply the input value from the weights and the h1. So how do you find h1? Okay, you have w1, w2, w3. How do you get it? So w1 multiplied by x1, you have w1, then x2 is connected to h1, x1 is connected to h1, x2 is connected to h1. So w1 is 0.15, so 0.15 multiplied by 0.05, then 0.20 multiplied by 0.10 plus the bias. So okay, this accumulation, so accumulation plus this bias is 0.35. So 0.0 multiplied by 0.15, 0.1 multiplied by 0.2 plus 0.35. What do you get? h1 1. So this is the pre-activation value. So how do you find the activation? Activation function what we are using here is sigmoid function. So sigmoid function, how do you find sigmoid function? Is 1 by 1 plus e power minus or 1 by 1 plus e power minus s2. So what is our s2 here? S2 is 0.3925, h1 is 0.3775, okay, h2 is 0.3925. Okay, you can find h1 as well as what s2. How do you find s2? 0.05 multiplied by 0.25, and what is the other one? 0.10 multiplied by 0.35 plus 0.35. This is how you compute what h1 and s2. How do you find? First we have computed pre-activation for h1 and pre-activation for h2. How do you find the how do you apply the activation formula? Activation formula here is sigmoid function we are used, 1 by 1 plus e power minus s2. Similarly for h1 you can compute 1 by 1 plus 1 by e power minus h1. So here s2 final is this one. Now we calculate the values of y1 and y2 in the same value as we calculated for h1 and h2. Okay, y1 again you form what is our h1 multiplied by w5. Yes, you can see here what is y1. Y1 is h1 multiplied by 0.4 and h2 multiplied by 0.45 plus the bias. The bias is 0.6 plus the bias. So y1. So how do you get y1 final? Again use the same sigmoid function, 1 by 1 plus 1 by e per e y1 final you can. Similarly you can find y2 final. So y1 final is 0.75 and y2 final is 0.77. But what is our target value? Target value is what? 0.01 and 0.9. So we are very far away. The value of y1, y2, we are very far. Our target value is a 0.9. Y1 has not matched the target value. So we find the error. So summation of target minus the output value. Target value, you know, we have just computed the output, predicted output from the model. So square, so of t1 minus 2, just you come substitute them and find e total. This is the total error. We back propagate this error. Back propagate this output. First you do it at the output layer. I give this, I will explain for the output layer, and for the hidden layer and then for weights and the biases you study on your own. So you subdate the weight error dou e total by dou w. We perform backward process to find. First consider the loss weight. Just so what's with we have considered w5 alone. Okay, dou e total by dou e w. So dou e total dou w, that can write as dou e total by y1 final into y1 final by y1 by w5. So we have considered what? This one w5 alone. So y1 final, you can write it, you are applying a chain rule there. y1 final by y1 final is the pre-activation is y1. So y1 in terms of what? w5. So first you are expressing in terms of y1 final, then y1 2. We are using the back propagation. Just we are moving in the backward direction. Calculate each term one by one. We differentiate. First you dou e total by dou y1 final. So e total is expressed to y1 final. Just you apply a simple. Just you find the derivative. Then you compute, then substitute them, and you can dou e total by y1 final. You can express as 1 by 1 plus e per minus s. Now you can compute y1 final by dou y1. Similarly, you can just you rearrange and you find out what dou y1 final by dou y1. Okay, then how do you express y1? Y1 is h1 final multiplied by w5, s2 final plus b2. So dou y1 by d, I am simply calculating all the derivatives and I am substituting them. So I will get dou e total by dou w5. Is substitute all the derivatives, I will get dou e total by w5. So now you update w5 new equal to w5 minus eta into dou e w5. Eta is a landing rate. I have set the landing rate as 0.5. This is a new value for w5. Okay, the initial value is 0.5. Now the new value is 0.5. Similarly, you can calculate the other values. This is w6, w7, and I have done for output layer, hidden layer, and the weights and biases. Study on your own. Now I will move to shallow to deep neural networks. So which is better, shallow network or deep neural networks? Okay, experiment shows deep is better. Either this is 1 layer, 2 layer, 3 layers. The number of layers, as the number of layers increases, the error rate decreases. You can see the table here. Not surprise, more parameters, better performance. This one is the shallow, is a very fat layer. This one is a deep, more number of layers are the deep layer, thin and tall. So same number of parameters, with the same number of parameters, which one is better? Definitely you will have higher the number of layers, lesser the word error percentage, word error rate. Okay, only one layer here more number of layers, higher the number of layers, so lesser word error rate. You can see here. So we have modularization is in deep learning is you are doing simple models. Simple, so we are dividing a big task into so many subtasks. We are, for each subtask we are assigning a model. That's module. It's called modularization. The image, you are doing some classifier, basic classifier, further classifier, like that. You are performing a deep learning there. So in that way performance will be enhanced. So classifier 1, classifier 2, classifier 3, girls with long hair, boys with long hair, like that. So lacking data and weak. So modernization. So when you have a shallow networks, that will be very weak. Okay, information is conditionally routed to subset of models and subsequently aggregated. First, we have a basic classifiers, then classifiers for the attributes. Each classifier can have sufficient training examples. Modernization or deeper reasons. Long hair, boys. So first we do the basic classification, then we, for each attribute we are having a classifier. Hidden nodes, modularization and features. The most basic classifiers we have here. Then the first layer as model to build the further classification. Second layer for second model, for the second model. So we are squeezing more number of layers for better performance. Modularization does automatically learn the less training data. Levels of features we have. Most basic classifier. This one, the first layer of model to build classifiers, the second layer, third layer, like that. So more and more classifications. First you have a basic classification, to do further classification, further attribute you classify, further attribute. So in this way you're deeper and deeper you will have. These are the references I have made. Thank you.